Now let's get back here. So we have come to understand that 2 pi radians is 360 degrees. So in that way we can be able to convert between radians and degrees, and with ease this time around. Now let's look at this example. Very important. Let's look at this example. Now he is saying that the radius of a particle moving along a circular path sweeps through an angle of 60 degrees at the center of the circle. So the radius of a particle moving along a circular path sweeps through an angle. So this particle has swept through an angle of 60 degrees at the center of the circle. Calculate the angular displacement of the particle in radians. So we know the angle in degrees, but remember the units for angular displacement is radians. So we need to find that. But now, first thing we know is that 2 pi radians is equal to 360 degrees. Therefore, what we're given here is 60 degrees. Will be what? It will be less. So we write 60 degrees divided by 360 degrees multiplied by 2 pi radians. Okay, so when you calculate this, it will be 1, this will be 6, 2 into this will be 3. What you'll find is that the answer is 1 pi over 3 radians, or you can say 1.05 rads. I hope I'm right with this, but yeah, you can confirm on your calculators if this is the correct answer, but it's supposed to be pi over 3 radians. This will be the angular displacement in radians. Very important. Okay, I hope that is clear. Now let's transition to something else. The second concept that we'll look at in this topic is the concept of angular velocity. Once again related to linear motion. In linear motion we had something called linear velocity, where we said linear velocity, which is speed in a particular direction, is linear displacement over time. Linear displacement over time. Remember, displacement is given the symbol s and time small letter t. So linear displacement over time becomes s over t. Now, owing to the same idea, that means in circular motion, okay, what happens is angular what? Velocity. Angular velocity is equal to, now instead of linear displacement it becomes angular displacement. We're talking about circular motion now, so it's angular displacement over time. Okay, angular displacement over time. Now the symbol for angular displacement is what we call omega. It looks like a W, but it sort of grows inwards on both ends. Okay, it's omega, which will be equal to, remember, angular displacement is theta and time is t. So this is the formula for finding angular velocity is equal to theta over time. Okay, theta over time, and remember this, angular linear velocity is s over t. Okay, just remember that. Okay, so we'll keep it here. Omega is theta over time, and s is equal to no, it's not s, it's supposed to be v, which is linear velocity, is equal to s over time. Okay, now I want us to look at something before we continue. When I talk about circular motion, okay, I just want to make sure we're together here. Okay, this is the center, and like that we displace from A to B. Okay, now let's take a particle is moving from there, then it's found there, then ends up at B. At each point, the linear velocity is tangent to the circular path. Okay, at that point the linear velocity is always tangent to the circular path at every point. Okay, always a straight line, v. The magnitude remains the same. Remember that the magnitude of the speed, or the linear speed, remains the same, but what changes is the direction in which it is going, the direction in which it is facing. At every point its magnitude remains the same, but the the direction changes. That is very important. The linear velocity is always tangent to the circular path. This is very important for you to remember. Now let's look at the other concept now. Okay, let's look at angular velocity and frequency. Angular velocity and frequency. Okay, let's do that. Okay, angular velocity and frequency. Now the thing I want us to understand is that remember, for one complete circular motion, the angular displacement we cover when we talk about one complete circular motion is literally 360 degrees, but in the actual units is 2 pi radians. Okay, that means we have made one complete circular motion. It means we have covered 2 pi radians. If we're talking about frequency and period, this one, let's go back to oscillation and waves. Okay, remember that frequency was the number of cycles per unit time. Okay, and the period was time taken for one cycle. That's period, time taken for one cycle. So if we have one complete circular motion, the time taken to complete that will be period. At that point, the time will no longer be time, just mere time. It will be time period. That is very important. The time taken for one complete circular motion. So if for one complete circular motion, the angular displacement is 2 pi radians, therefore the time will be equal to period. Capital T is periodic time. Okay, therefore we want to establish a relationship between angular velocity and frequency, in case some of you are like, what is happening? Okay, so we remember that angular velocity is equal to theta over time. So for one complete circular motion, the angular displacement will be 2 pi radians over the time period, which is capital T. Okay, in this case I can just remove the units, it's fine. Okay, let me write it properly. So it will be 2 pi over time period, but frequency is equal to 1 over time period. Therefore angular displacement will be equal to 2 pi f. Okay, why? Because this 1 over t, the t that is there, can be written as 2 pi times 1 over t. This part is this. That's why we've substituted it here. Okay, let's become just that. Now that's exactly what happens. That's a relationship between angular velocity and frequency. All right, so this is very important for you to understand, and I think after this we'll go to part 2 of this lesson, and we'll talk about the relationship between angular velocity and linear velocity. Thank you so much for watching. Be sure to watch the next video. Thank you.